Hey guys, this is November 23, paper 2. In this video we will be looking at the first question, which is mainly related to kinematics and the gravitational part of the syllabus. So in this first question, we are told that we have a space probe of mass 95 kilograms and we are at the surface of an asteroid with a specific acceleration, which is the gravitational field strength here. So it's important in later questions that we don't consider the g to be 9.81 like on Earth, since we are not on Earth. So in the first question we are told to calculate the mass of the asteroid. We're given the radius of the asteroid. So here we simply need to apply the formula that we can find in the data booklet, and g is equal to the gravitational constant times m divided by the radius squared. We can rearrange this for the mass, and then we will find that this will give us the mass. Since we know the gravitational field strength and we know the radius, and as I said, g is just a constant, so if we plug in all the values, then we will find that the mass is 2.1 times 10 to the 18. Also important to look at the significant figures given in the question so that our final answer will match the significant figures. As we can see, the question only gave us two significant figures. For example, in 2.7, only two significant figures, also in 95. So the least number here is 2. So we want to give our answer also to two significant figures, which we can do by writing it in this format, so that this 2.1 is two significant figures. And then we also want to make sure that we include our units, which in this case is kilograms. All right. So in part B, we were told that this probe is this probe is carried onto the asteroid, and we simply need to calculate the weight of this probe when it's close. And well, we were given the gravitational field strength close to the surface, and we were given the mass, so we can simply use the formula F equals mg. Important to remember here not to automatically put in 9.81, since we are not on Earth, as I said previously. And so this will give us like 2.565 times 10 to the minus 1. But again, we want to consider our significant figures. We only need two significant figures, so we can either write 2.6 times 10 to the minus 1 newtons, or 0.26 newtons also works in this case. So in part C, we are told that the probe approaches the surface of this asteroid, and they fire a rocket engine to slow it down, and we need to explain why this is the case. And as you can see, this is 3 marks, so we need to write quite a bit, and we are given quite a lot of space. So these are just hints that you probably don't want to just write one line as an answer. But so why this is the case? I mean, there are multiple ways to explain it. I would say the simplest way to explain it is that the engine is exerting an upward force on the rocket. So first of all, the engine exerts an upwards force, simply because it is pushing down the burn fuel, and that generates an upward force on the rocket. And this force is larger than the force due to gravity on the planet. And since this force is larger, there will be a net force acting on the aircraft than the gravitational force. And since, if we make a small little diagram, like let's say this is the probe, and then we can draw in gravity, Fg, and then we can say this is Fe, E for engine. Then we can say that the force exerted by the engine is going to be larger than the force due to gravity, and therefore we will have a net force pointing upwards. And what this means is that we will also have an acceleration. Since we know F equals ma, if we have a net force, then there must be an acceleration. And since here our net force is pointing upwards, it also means that our acceleration, so to say, is also pointing upwards. So pointing upwards means that it is slowing down. It is accelerating away from the planet, meaning it is descending, so it's losing its speed. So yes. So there is also an acceleration, and so due to this, we have a decreasing speed. And so this is how it slows down. As I said, there are also other ways to explain it. I think this is the most general one. I think you can use this explanation in other styles of question, but you can also obviously use Newton's third law of like the equal and opposite reaction forces. But yes. And then we are told that this rocket force is 12 newtons, and we must deduce the, well, we need to deduce the time it needs to fire to slow it down from an initial speed of 0.64 to a speed of 0. And here we also need to use an appropriate number of significant figures. So here there are probably two main approaches you can take. I'll try and show you both of them. So the first one, well, first of all, we can again make this small little drawing we made in the previous case, where we have the gravitational force and we have the force of the engine. And we know the value of both of these, so we can say that the net force will just be the sum of these two forces. And since the gravitational force is pointing downwards, we will account for it as being a negative force, as they point in opposite directions in this case. So this will just be the net force. In the previous part, we have calculated that the weight is 0.26 newtons. So we can do 12.0 minus 0.26, which will give us that the net force is 11.7 newtons approximately. And yes, so now we know the net force, and from Newton's second law we can also know that the net force is just the mass times the acceleration. And we also know the mass. This was also given to us in the first part of the question, 95 kilograms. So we can just plug into this equation. So we will find that the acceleration is just 11.7 divided by 95, which will give us approximately 0.12 meters per second squared. And now we know that this is the acceleration. We can use the simple equation that the acceleration is the rate of change of velocity. So acceleration is delta v over delta t. And if we know this, well, we know the acceleration and we also know the change in speed, since this is just from 0.64 to 0. And so the only unknown we have now is the change in time, the time it took for it to slow down from the speed of 0.64 to a speed of 0. So we can say that the time it took is just the change in velocity over the acceleration. So that will be 0.64 over 0.12, which will give us approximately 5.2 seconds. And so that's how it will that's how much time it will take. And also here we can see two significant figures. Usually we always want to make sure that we use the least number of significant figures provided. Especially we want to make sure we do so when they highlight in the question, because probably one of these 4 marks will be one of these 4 marks will be for using the correct number of significant figures. So these are always easy marks to get. Now we move on to a slightly different part. We need to show this equation is true. This is, I believe, part of the theme D and D.2, where we need to use some of the formulas listed in the data booklet. And well, the main formula we need to use obviously is the escape velocity, which will be just 2gm over r. This is from the data booklet. And well, we see that we have some similarities. So for example, this 2 is already here. So we probably just want to somehow manipulate this part of the equation to make it look like this g times r. And if you're unsure of what to do here, what I would recommend is just go through some of the equations in the data booklet and see if we can plug in anything to rearrange this equation pretty much. And if you notice, we can see that g, we've actually already used this equation previously in this question. We know that g is simply equal to gm over r squared. So if we try and plug this into the escape velocity equation that we were given, we can see that the escape velocity is simply the square root of 2 times this what we have found, so this gm over r squared, which is just g, times r. And if you notice, this and this are identical, since I put an extra r multiplier there so that the r's cancel out. The r squared and the r will cancel each other out, since one of them is on the numerator, the other one's on the denominator. And so now, so this is the solution. This is how we can rearrange it like this. You could also try do it the other way, I think, where you try and start from this equation, or maybe, well, for you to like try and see if you're unsure of what to do, you can also try and go the other way. So you know you were given this equation and you try and go back in this other way. Obviously this is not the solution you want to write down, but if you have like a scrap paper, you can just think about this method, and then afterwards when you have figured that out, you can write it down the opposite way, which we have done over here, because we always want to start from the equation that we know, and our final equation we give should be the equation that we need to show in the question. And so now we need to just simply calculate the escape speed of the asteroid. This is again very common in IB, where we need to show something and then use it in a later question. This is usually the case when we have a show that question. Whenever there's a show that at the start of a sentence, it usually means that we will need to use this result in a later question, and that is no different here, as we can simply use this simplified equation. That is why we have to show it, so that we can make our lives a little bit easier. So we can just plug it in. We know g again is not 9.81, it's 2.7 times 10 to the minus 3, and we know that the radius was 230 kilometers, which in meters is going to be 230,000. So we want to try and stick to SI units here. So this will just give us 35.24 meters per second, which again, the 2 significant figures here is going to be 35 meters per second. Again, don't forget the units. And then the last part of this question is kind of completely unrelated. This is just a simple mechanics question that can come up often, also in different styles, but the idea is always the same. Here we're simply given a stone at some height, and we are told that it's launched horizontally with a speed of 34 meters per second. What's important here is that there is no vertical speed. We don't have any initial speed in the vertical direction. Speed initially. So this will make our lives a little bit easier, as we don't need to account for that. But as always, as in all these types of questions, we want to simply separate the x and the y direction, as they are independent. It doesn't matter how fast we are launching the ball, it will land always in the same amount of time. So it doesn't matter if we're launching it at 100 meters per second horizontally or 5 meters per second horizontally. If it's at a height of 1.9 meters, it will always land after the same amount of time. This is what it means that the vertical and horizontal components of the displacement and velocity are independent of each other. So knowing that it's at a height of 1.9 meters, we can calculate the time it takes for it to land, which you can do so with a formula from the kinematics from the very beginning of the syllabus, which is going to be this formula. Since here we know that the initial speed is 0, so this term just cancels out. We know the displacement, we know the acceleration, and what we need to find is the time. So we can just say that 1.9 is equal to 1/2 times, again, not 9.81. We are still not on Earth. And then this will be just t squared or x squared, doesn't really matter. And then if you plug this into your calculator or rearrange and take the square root, then you will find that the speed is 37.51 seconds. Here it's not important to convert to two significant figures, since this is not our final answer, and if we keep more significant figures during the calculation, then our final answer will be more precise, and then we can round that off in a more precise manner. Now we are just one step away, as we know the speed it took to land, and we also know the speed that is going horizontally. So what's important to see here is that we have no acceleration in the x direction, which means that it's not going to be slowing down whatsoever, as there is no air resistance in this problem. So if we know the time it travels in the air for, and if we know the speed that it traveled this distance for, then well, we can use probably the most basic formula in the syllabus, that the speed is equal to distance over time. So from this we can just see that if an object travels at constant velocity for some time t, then the distance it will travel is just v times t. So 34 times 37.51, which if rounded will give us 1,300 meters, again to two significant figures. So this was the end of the first problem in the 2023 November paper 2 paper. I hope I was able to help, and see you in the next one.